Okay, so machine learning is increasingly influencing sensitive decisions about individuals in domains such as housing, education, employment, and criminal justice. And while machine learning has the potential to substantially improve the quality of predictions in these areas, these decisions can have a significant impact on people's lives. And as machine learning becomes more and more commonplace, there have been numerous instances in which machine learning models are, or at least have the appearance of being discriminatory against certain groups of people on the basis of factors such as gender or race. And in some areas, such as criminal sentencing or housing, the necessity to, there are abundant moral and legal reasons why we can't tolerate this sort of discrimination. And even in other areas where maybe the stakes seem less high, there are still good reasons why we should guard against systematic discrimination. And so to this point, it's not exactly clear what I mean by discrimination. This is a word with very complex and nuanced meaning in common parlance, and in order to apply this in machine learning, we need something more precise. There's been quite a bit of debate in recent years on how best to define discrimination for use in machine learning. We, in our work, focus on one particular setting, supervised learning, and on a particular notion of discrimination suited for that setting. So in this setting, the learner is given access to n samples from a distribution, and these samples are composed of the following three parts. So there are x, these are general predictive features. We also have access to a, this is the protected feature, this is what we want to avoid discriminating with respect to. And finally, there's y, this is the target of the prediction task. So the goal is to find a predictor from a hypothesis class. This predictor can use both x and a, and we want it to be good with respect to a particular loss function. So I'd like to emphasize here that we have this fixed y, this fixed measurable y, and we know this in advance. And this is kind of the standard supervised learning setting. We do not necessarily cover every possible place in which you'd want to avoid discrimination with this, but that's what we're working with. Similarly, we assume that we know A in advance, and this is the only thing that we're worried about discrimination with respect to. The definition of discrimination we work with is known as equalized odds. It was proposed by Hart et al. Last year, and it says that a predictor is non-discriminatory with respect to A if the predictions made are conditionally independent of A given the truth Y. And on a more intuitive level, what this is saying is that the predictions reveal no more information about A than what is already contained in the truth. Similarly, in the case that the predictions in A and Y are all binary, which it will be in this talk, this is equivalent to requiring that the false positive rate is the same both when A equals 0 and when A equals 1, and similarly for the true positive rate. And this is the view that will be most commonly referred to in this talk. So this is nice. We have this definition of non-discrimination, and we can take a predictor and evaluate whether or not it is non-discriminatory. In the work which presented this definition, the focus is generally on defining it and on the implications of the definition. In our work, we focus on the more practical question of how do we learn a non-discriminatory predictor from a finite sample of data. So the essential question is, if I have n samples, how accurate of a predictor can I find, and how non-discriminatory will it be? And this is both a statistical question and also a computational question, and we address both. So Hart et al. Take a kind of first step in this direction with something I'll refer to as the post hoc correction algorithm. And this algorithm takes a predictor, y hat, and it corrects it to be non-discriminatory, even if it wasn't discriminatory to begin with. And it does so through a constrained optimization problem. Effectively, what this is doing is it takes the predictor and it looks at the joint statistics of that predictor with A and Y, and it sort of factors out the discriminatory part of the predictor while also optimizing the loss at the same time. And this algorithm is nice because when the predictions in A and Y are all binary, this is a linear program in 4 variables. So it's very easy to solve. And even when Y is real valued, this can be solved efficiently. Additionally, it only depends on the joint distribution of Y hat with A and Y and does not require use of X, which can be useful in certain cases. So the existence of this correction algorithm suggests an approach to learning a non-discriminatory predictor. So we can start with your favorite learning algorithm. We learn a predictor without worrying about non-discrimination. You don't need to change your code. You can do whatever you're already doing. And then afterwards, we apply this post hoc correction to the predictor to get a new non-discriminatory predictor. And this is nice. You will get a non-discriminatory predictor, but there's a catch, which is that the predictor you get can have extremely poor accuracy, even when there's a good non-discriminatory predictor in your hypothesis class. And so an example of how this can happen is based on the following distribution over 2 binary variables, one of which is equal to A and is extremely well correlated with Y. The other one is slightly less correlated with Y, but it's conditionally independent of A given Y. So if we look at what the optimal predictors are in this distribution with respect to the 0-1 loss, X1 is the optimal unrestricted predictor, and X2 is the optimal non-discriminatory predictor. And these have 0-1 error, epsilon, and 2 epsilon respectively. So in this algorithm I just proposed, the first learning a predictor and then correcting it, we might start with the optimal unrestricted predictor. So let's look at what the post hoc correction of this is. The inputs to the predictor are the predictions, which are x1, which is equal to A, and A. So the only real input to this is A. And in order to be non-discriminatory, we can have 0-1 error, at best 1/2. So this is somewhat disappointing because we have this great predictor that has error only epsilon, yet when we apply this post hoc correction, we lose all of the accuracy, even though there's this nice non-discriminatory predictor on this distribution. And so the moral of this story is that we can't avoid the question of discrimination in training the predictor. We really have to account for that at the beginning. So a straightforward approach to doing this is we take our sample, we find the best predictor on the sample, and then we do this subject to a constraint that the predictor is non-discriminatory on this sample. And from this we can obtain a guarantee. The risk bound matches the standard PAC learning upper bounds. And we can also get a guarantee on the non-discrimination measured in terms of the difference between the true positive rate for different values of A and also the false positive rate for different values of A. And this is bounded by a term that scales like VC dimension over N. And this VC dimension part of the bound is what I'd like to focus on. This is perhaps troublesome if we really want to have an extremely non-discriminatory predictor. This could be painful if the complexity of the hypothesis class is high. And it turns out we can actually get rid of this dependence using the following 2-step procedure. So first, we take our data, we split it in half, and we use the first half of our data to find the empirical risk minimizer with a non-discrimination constraint. With the other half of our data, we apply this post hoc correction to the output of step 1 to get a non-discriminatory predictor. With similar analysis to before, we can get an excess risk bound, which is like before, and also we can bound the excess discrimination with a term that does not depend on the VC dimension any longer. We also can show a lower bound, which shows that this dependence on P min is necessary. And essentially, the reason this is true is that in order to get non-discrimination, we need these true positive rates to match for different values of A, and also the false positive rates, which means we need generalization on all of the combinations of Y and A. So we need samples that scale with the smallest probability of those. So as a quick sketch of the proof, we get concentration on the 0-1 loss and also on these A conditional true and false positive rates. The kind of tricky part is in moving from step 1 through the post hoc correction in step 2. And what we're worried about is that, as in the example I showed earlier, that we're going to hurt the loss significantly. It turns out that this doesn't actually happen, and the reason is because of this key lemma, which says that if I have a predictor which is almost non-discriminatory and has loss L, then the predictor I derive from it with the post hoc correction will have only slightly worse loss, L plus alpha, where the approximate non-discrimination is defined again in terms of the difference in the true and false positive rates. So as in PAC learning, we have this nice answer to the statistical question of learning a non-discriminatory predictor. This is fairly complete and satisfying. Unfortunately, the computational question is hard. As you might have imagined, this step 1, the constrained DRM, is computationally intractable. And this happens even when the hypothesis class is linear predictors and when the loss is convex. And effectively, the reason that this happens is that the non-discrimination constraint can be used to encode minimizing a 0-1 loss. And through that, we can reduce agnostic improper learning of half spaces to performing step 1 of the two-step procedure. To conclude, our work also presents a relaxation of the equalized odds definition of non-discrimination, this time based on a second moment condition rather than a conditional independence condition. The two are equivalent in the case that the data x, a, and y are all jointly Gaussian. And we show that this definition of non-discrimination leads to a tractable version of the two-step procedure, and we can also get a similar guarantee in terms of accuracy and second-order non-discrimination. So in conclusion, our work shows that the post hoc correction proposed by Hart et al. Alone is not sufficient to get a predictor that is both non-discriminatory and accurate. We show that ERM with non-discrimination alone, without this post hoc correction, results in a suboptimal dependence on the VC dimension in the non-discrimination bound. And we show that together, these two, the two-step procedure will get us a predictor which is both non-discriminatory and accurate at the same time. And we also show hardness of the two-step procedure and present a relaxation of the definition of non-discrimination. For more details on this and also a few other things that weren't covered in this talk, please come to our poster. I'd love to see you there.
Which step of the two-step procedure was hard? Can you repeat?
He asked which step of the two-step procedure is hard. It is the first step, the ERM with the non-discrimination constraint. Oh.
Can your algorithm be non-discriminatory for many different groups at the same time?
He asked if the algorithm can be non-discriminatory for many different groups at a time. Do you mean for A that's not binary?
For different A's.
For different
attributes.
So you need to know what A is in advance to perform the post hoc correction, for instance. But if A is more than binary valued, if it takes on many values, you can still be non-discriminatory with this algorithm.
I think he was asking about different attributes at the same time. Say, I want to be non-discriminatory with respect to race, and I want to be non-discriminatory
Oh, I see.
gender.
So
Several of those at the same
one thing you can do is you can make A vector valued, and you can have each component of A correspond to a different attribute. And then, again, this is kind of the same as having it take on multiple values, but you can account for that. Yes.
Okay, let's take the speaker again.